So last time we talked about spherical and Cartesian coordinate systems and how their vectors, their unit vectors, relate to each other. So we talked about how Cartesian unit vectors don't change no matter what point you're looking at, but spherical vectors change depending on the point. So now we want to know how to find a relationship between spherical and Cartesian coordinate systems. So to do that, we're going to use a technique called projection, or a term that I think is more intuitive is just squishing. So if we have a point P out here, and it's got coordinates, again, x naught, y naught, z naught, and it's also got coordinates r naught, theta naught, phi naught, or just r theta phi. I might drop the zeros just so I don't confuse people. So if we project it, and right now what I'm doing is projection. So it's got a certain height z or z naught. It's got a certain x coordinate x naught, a certain y coordinate y naught, and it's also got a coordinate that I'm going to introduce rho naught. And rho is used. Rho is a cylindrical coordinate. It's used to measure just the distance from the origin to the xy, to the edge, to the corner of the xy coordinate, basically. And you've also got your theta. I'm going to drop the naught notation because it's getting kind of annoying. And you've got your phi. So how do we get the relationship between the unit vectors themselves? Well, to simplify this whole thing, because we don't want to deal with 3 dimensions at once, we're just going to deal with the xy plane. So we're going to pretend, actually we're going to enforce that theta is equal to pi over 2, or 90 degrees. And doing this will let us tease out the relationships between x, y, and phi while we ignore theta, and then we'll come back to it later. So if all we care about is the xy plane, and I'm going to draw it in a way that you're probably not used to, but it sort of corresponds to the way that I've drawn it above. So imagine we're looking at this 3-dimensional coordinate system from above. We see our y coordinate pointing off to the right and our x coordinate pointing towards us, or here I've drawn it as pointing down. And again, we've got this line rho. We've got our angle phi, and we've got our distance, or sorry, that's not it's not x, that's our distance y naught, and our distance x naught. Now, if we draw the unit vectors, let's draw the cylindrical unit vectors. This is actually going to make our life much easier. So rho hat is just pointing in direction of increasing rho, and it's the r hat vector but projected onto the xy plane. So that's rho hat, and then we've got our phi hat vector, which is pointing in direction of increasing phi, and it's always perpendicular to rho hat. And that's something that I should have mentioned earlier. These unit vectors are all perpendicular to each other, so they're not linearly dependent in any way, and they're orthogonal. Okay, so what does this tell us? Well, right now it doesn't tell us a whole lot, right? It's sort of not entirely obvious where we should go. But if we twist this, so let's take this line and let's twist it down here. So let's pretend that the line ends at this point. And if we draw rho hat, then rho hat is like that, and phi hat is pointing in that direction. And that's nothing but our xy unit vectors at the same location. So that's interesting. So we can immediately write that the x hat vector is equal to the rho hat vector, but only when the angle phi is equal to 0 degrees. And what function do we know that satisfies that? We know that cosine of phi does just that. So when phi is equal to 0 degrees, then the rho hat vector is the x hat vector. And we can write something similar for the y hat vector. Y hat is just phi hat times cosine phi. And we don't know what dependence on theta is, so I'm just going to write a little f of theta out here times f of theta. But we know that this is the phi dependence for x and y in terms of rho hat and phi hat. But what if we turn the vector, or we turn our line the other direction? So let's turn it up here. So this is our new point. Then our rho hat vector is pointing out this direction, and our phi hat vector is pointing out this direction. Well, that's also interesting. So that tells us that at this point, our x hat vector is just equal to the negative phi hat vector. So at this point, x hat equals minus phi hat. So we wrote that x is a function of rho hat, but it's also a function of phi hat. So it's equal to rho hat times cosine phi times some function of theta minus phi hat. And what function do we know where when phi, and this is where phi is measured from, when phi is 90 degrees, this the function, the dependence on phi is equal to 1. Well, that's just sine phi. And here we're implicitly assuming that all of our dependencies are in the form of sine and cosine. And that's always the case when you're dealing with uniform circular motion. So when anything you're dealing with rotates in a circle, you're always going to end up with just sines and cosines, which is cool. But we don't know the dependence on theta again. So this is also times some function of theta. And y hat is nothing but, at this location, it's just equal to rho hat. So let's say plus rho hat, and this is also sine phi, because phi is equal to 90 degrees, y hat is equal to rho hat. And I'm just going to write on here, this is, remember what y hat looks like, and this, that's negative x hat, what am I doing? That's y hat, and that's x hat at all points on our little graph. And this is multiplied by some function of theta. We don't really know what it is. Okay, so where would we expect our theta dependence to show up? And the way that I've written it here, it's perhaps a little misleading. We said that we were going to flatten our r hat vector, right, and make it into a rho hat vector. And that is actually where our theta dependence will come from. So it's not that this whole function is multiplied by f of theta. It's that rho hat itself is a function of theta. And what is the function of theta? Well, if we just draw our vector system again really quick, we can try and figure it out. So if this is our, again, our x coordinate, our y coordinate, and our z coordinate, and we've got our point, we project it down, we had our initial r hat vector, and then we have our rho hat vector. And to figure out how they depend on each other, we're going to do exactly what we did above. We're going to see what happens when theta equals pi over 2. So when theta equals pi over 2, or 90 degrees, this line here, and I'm going to draw this line in green, this line is exactly the same as the projected line, and rho hat is exactly the same as r hat. So rho hat is just equal to r hat when theta equals 90 degrees, and the trigonometric function that does that is sine theta. Um, and so that is our dependence of rho on r. But we have a problem here, and that's that rho hat is always supposed to be unit length no matter what happens. And that's clearly not the case here. So how do we fix that? What did we miss? Well, we only looked at the dependencies when theta equals pi over 2. When theta equals 0, then our line is pointing vertically, and our r hat vector, our r hat is pointing straight up. Our rho hat, it's not really clear in which direction it's supposed to be pointing because it's supposed to point out from the origin to the point. So let's move this line just a teensy tiny bit to the right. Let's say that our line is actually here. Then rho hat is pointing out like this. It's almost completely straight. And our theta hat vector is pointing in the direction of increasing theta, which is in the same direction as rho, or almost exactly the same direction as rho. So as you get closer and closer to the origin, rho hat and theta hat will become exactly the same. So what trigonometric function do we know that's equal to 1 when theta is 0? Well, that's just a cosine. So r hat sine theta plus theta hat times cosine of theta. And this is complete. And if you want to convince yourself of that, then you just take the dot product of rho hat with itself to find its magnitude. And that's just equal to, well, this is the magnitude squared. And that's just equal to sine squared theta plus cosine squared theta, which is equal to 1. And what's the square root of 1? Well, it's just 1. So that is the complete description of rho in terms of r hat and theta hat. So if we go back to our original set of equations, x hat and y hat, we now know where this f of theta comes from. So it's not, again, it's not that it's multiplied by some f of theta, it's that rho hat itself is a function of theta. And we didn't know that when we were first writing out this set of equations. So um, I couldn't really justify writing that f of theta, but I wasn't sure what the dependencies were, so we just wrote it like that. So if we rewrite these equations, then x hat is equal to rho hat, which is just r hat sine theta plus theta hat cosine theta times cosine of phi minus phi hat times sine phi. And this phi hat, we don't know if there doesn't appear to be any theta dependence, but just to make sure, we could take the dot product of x hat with itself. And why don't we do that really quick, just to make sure. So we dot each component of the vector with itself. So the r hat component is just multiplied by itself. So sine squared theta times cosine squared phi. The theta hat component is cosine squared phi, or cosine squared theta, sorry, times cosine squared phi. And then the phi hat component is nothing but sine squared phi. And the negative cancels out because it's squared. Well, if we factor this, then we see that we have cosine squared phi times sine squared phi plus cosine squared phi, which is just 1, plus sine squared phi. And these two together are just equal to 1. So we see that no matter what theta and phi is, the x hat vector in this way is always of magnitude 1. So our description is complete. And the same is true for the y hat vector. So if we rewrite this out in fully expanded form, x hat is just r hat sine theta cosine phi plus theta hat cosine theta cosine phi plus phi hat or sorry, minus phi hat sine phi. This is a minus sign. Y hat is, and we just plug in rho hat equals what we found before. And so we get r hat sine theta sine phi plus theta hat cosine theta, sorry, that's theta, cosine theta sine phi plus phi hat cosine phi. Now we could dot it with itself just to confirm that this is correct, but honestly I don't really want to. So I'll leave that as an exercise for you if you like. And the only thing that we have left is the z hat vector. Now, throughout this video, um, all we've basically done is varied theta and made it equal to some pretty obvious or easy to evaluate values, and then figured out the phi dependence, and then we've set phi to a certain thing and figured out the theta dependence. And that's exactly what we're going to do for the z hat vector. So we've got our coordinate system, and I'll give you one guess as to where we're going to start. That's right, we're going to start with theta equals 0. So if we draw a line, theta equals 0, then the z hat vector is pointing straight up. So is the r hat vector, because it's pointing away from the origin. So I've drawn them right next to each other, but they're the same exact vector at that point. So z hat is just equal to r hat. And what trigonometric function is equal to 1 when theta equals 0? That's just cosine of theta. And this is essentially the same exact way we've done it throughout the rest of the video. But this is clearly not the entire story. What about phi dependence? And this clearly isn't of magnitude 1 for all theta and phi. So let's take theta equals pi over 2. Well, r hat is pointing, or z hat is still pointing straight up. R hat is pointing straight away, and it's equal to rho hat. We know that from before. And this is theta. And theta hat is pointing in the direction of increasing theta, which is straight down. So the theta hat dependence is just minus theta hat times sine theta. And we're not sure at this point whether this is complete because it might have phi dependence. So it actually doesn't, and that's really interesting. It's not immediately obvious why. So if we draw some arbitrary point P, and let's just erase this stuff real quick so that we can have a better picture of what's going on. If we draw some arbitrary point P, and we just project it, and yada, 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 we've got phi and theta. If we have a certain theta, as we vary phi, this point will trace out a circle in the xy plane. And the phi hat vector, initially it's pointing sort of off in this direction, and that's sort of out directly away from us. Here it's pointing in this direction, here it's pointing in this direction, but at no point is it pointing up or down at all. It's always pointing just perpendicular to the circle because it's the phi hat vector that points in the direction of increasing phi. So the phi hat vector doesn't point up or down at all. It's only ever pointing in the xy plane. And you could see this just by projecting things onto the xy plane. The phi hat vector is always pointing just straight out or straight in the xy plane. So there is no phi dependence of the z hat vector. And we have our complete set of equations. So z hat is just r hat cosine theta minus theta hat sine theta. And we're done. Those are our dependencies. And if you want, you can, I'll make another video going back the other direction, but it's much, much simpler than what we've just done in this video. But the main thing I want you to take from this video is that not these final formulas, but the method of getting to them. It's actually really simple. We just look at different planes. So we look at, okay, what happens when theta equals 0? What happens when theta equals pi over 2? And we're essentially able to figure out the dependencies that way. So if you ever forget, was there a cosine phi here? Was there a cosine theta there? You can just use this method to quickly figure out what it was you forgot. And this is a much better way, in my opinion, than just memorizing formulas.